Welcome to lesson 2 of the S1 revision workshops. Today's lesson is going to be looking and introducing some new probability ideas. Today we're going to look at the ideas of set theory. Before you start, it's a good idea to make sure that you've got, if you can, print out the presentation slides. If not to worry, you can get these later on. But please make sure you've got a pen, paper and calculator to hand, because you will be expected to have a go at some of the questions in the presentation. Okay, so these are the S1 topics. As you can see, today we're focusing on probability and introducing set theory. Discrete random variables and the other topics are to follow. So, today we're going to be looking at Venn diagrams, what Venn diagrams are and how we can work with Venn diagrams to make probability problems easier to solve. Essentially, a Venn diagram organises logical sets by encompassing them inside different areas of the diagram. So this oval shape here, this would contain all the elements that would relate to a certain set that we would call A. This oval here will contain all the elements that relate to a certain set B. Outside of the Venn diagram contains the remaining members from a population which are not linked to the set A or the set B. And in this overlap here, we call this the intersection. This would relate to the members that are in both set A and set B. Our Venn diagrams can be used to organise information in such a way that it's easy then to get further information from them. So if we start off with a problem, if we consider rolling a six-sided dice, if we say the event A is rolling an even number and say the event B is rolling a prime number, we want to state the sample spaces and represent the sets in a Venn diagram. So here we use S to represent the sample space. That represents all the outcomes. So what I want to do is list the outcomes for rolling a six-sided dice, which is simple enough. 1, 2, 3, 4, 5 and 6. So these are all the outcomes. This represents our sample space, or our population, as I mentioned a moment ago. The event A was rolling an even number, so I want to list all the outcomes from the sample space which are an even number, which is just 2, 4 and 6. Event B was rolling a prime number, so I then want to list all the outcomes from our sample space that are primes. 1 is not a prime, it's square, it's triangle, but it's not a prime number. So we start with the smallest prime, which is 2, the only even prime. The next prime is 3, and the next prime after that is 5. Now, when I organise this into my Venn diagram, each of the numbers from the sample space, 1, 2, 3, 4, 5, 6, must be contained within the rectangle, because this represents the entire sample space. Within the oval A, all the elements 2, 4 and 6 must be listed. Within the oval B, all the elements 2, 3 and 5 must be listed. Any remaining elements must be listed around the outside of the two ovals, and any elements that are in both sets must be listed within this intersection of the sets. So if we start with this central part of the diagram, this is essentially the key to Venn diagrams. The only outcome that is in both sets is the number 2. So I'm going to put the number 2 in the middle there. Then if I look at the set A, the remaining elements of set A are 4 and 6. If I look at the set B, the remaining elements of set B are 3 and 5. And then finally, the only remaining outcome is the number 1. So this is one way to use a Venn diagram. You won't necessarily be expected to use a Venn diagram in this way in the S1 exam. It's just a nice way of introducing the idea of a Venn diagram and how it can organise sets for us. From this we could ask different probability questions, but I'm going to stop there because we'll go into probability now. Okay, so as it says here, Venn diagrams can also be used to represent the proportions of different sets. This means that they can be used to answer different probability questions. So if we just go back to our previous example very, very briefly and have a look at this, what I could have done instead of listing the actual elements was write the proportions here. So how many are in the set A and the set A alone? Well, that would have been 2 out of 6. How many would have been in the intersection as a proportion? That would be 1/6. How many could we represent the set B only in set B as a proportion? 2 out of 6. And then how many could I represent as just not being contained within those sets? 1/6. So actually, instead of listing specific elements, what we can do is we can list proportions of the elements, and that way we can solve probability problems. So let's have a look at example 2. Example 2 says, in a class of 60 students, 37 are in the mathematics team, 39 attend code club, and 25 take part in both the mathematics team and the code club. A student is chosen at random. Find the probability that the student is in both the mathematics club and the code club, is in neither the mathematics team and code club, is in either of the mathematics team or code club, but not both. Okay, so I can use this Venn diagram to help us with this question. What I'm going to do is, instead of actually putting the individual elements in, I'm going to put the proportions of the elements in. So the first piece of information we had was that 37 are in the mathematics club. I'll just list it across the top to remind us. We then had the next information that 39 were in the code club. And then finally we had 25 in both the mathematics both in the mathematics and code club. So it's 25 in the mathematics and code club. Okay, so if I list these elements into my Venn diagram, let's call the oval on the left the mathematics, let's call the oval on the right code club. I'm just using, hopefully you've noticed, the initials to represent these, nice and logical. So in mathematics and code club, in this central part here, the intersection, which as I said before is the key to this Venn diagram, I can put a 25. Then in the mathematics club, let's go back to black, apologies. Then in this mathematics club, the elements in this part of the oval representing the mathematics club and this oval must total 37. So that must mean that what goes in this section here is the difference between 37 and 25. So there are just 12 students in the mathematics club and the mathematics club only. Similar idea with the code club. We want to know there's already 25 in the code club, but they also attend mathematics. So how many just attend the code club as alone? Well, it would be the difference between 39 and 25, which equals 14. Finally, we were told initially that there were a total of 60 students. So 60T for 60 total. So if I want to know how many students are not attending any of these, first of all, I total up the inside. So that would be 37, that would be 51. And so I want to find the remaining students from 60 that are not in these sets already. So 60 minus 12 minus 25 minus 14 equals 9. Okay, so now I know exactly how many students are in what club. I can answer my probability questions. You can, if you want to, convert these straight away to probabilities by writing them just over 60, like we did a moment ago. It's not strictly necessary, a little bit messy now that I just focused on the numbers. It's completely up to yourself. Okay, so probability in the maths club and the code club, well, that's just reading that intersection out. So I've got 25 over 60. Haven't cancelled them at the moment, and you'll see why in a moment. So I mean, now I'm giving my final answer. I could cancel this. This would be 5/12. Probability that they're not in the maths or the code club. Well, that's these 9 students that are not contained within those sets. So it's 9 out of 60. Again, I'll cancel this at this point so I can divide top and bottom by 3 to get 3 over 20. Finally, the last one was maths or code club. I'm just going to write underneath as a reminder, but not both. Okay, so you can either be in the maths club, so you could be these 12 students here, or you can be in the code club, so you could be these 14 students here, but you can't be in both. So this is why I haven't cancelled, because actually what I'm doing is those 12 plus the 14, so the 12 from the mathematics club only, plus the 14 from the code club only, so I get an answer of 26 over 60. And at this point now I've got final probability, I cancel 13 over 30. Okay, I hope that all made sense, because now here's one for you to try. So, in a small sixth form of 50 students, maths and English are the 2 most popular subjects. 30 students are studying maths, 25 students are studying English, 10 students are studying maths and English. Find the probability that a student chosen at random is studying maths or English. And I think let's just clarify this. So that'd be fine, maths or English. Okay, so what I'd like you to do at this point is I'd like you to draw a Venn diagram and work out that probability. But before you do so, pause the recording now and attempt this as I've stated before. You unpause and see my solution. Okay, well, I hope you've had a good go at that and that you've managed to get to grips with it. So if you remember, we have 50 students in total. We know 30 students are studying maths, 25 students are studying English, and 10 students are studying both. So let's put 10 students in the middle. We know that that is 10 out of 50 students. Let's label up the ovals just to make it clear which is which. So M and E for maths and English. We then had 30 students who are studying maths, so that means the difference here, these have got to total up to 30, so I'm going to get 20 over 50. English students, there are 25 students studying English students, that must mean that I've got 15 remaining in this section in order for the 2 parts to add up to 25. And finally, how many students on the outside? Well, there's a total of 30, 45 contained within the maths and English sets, so that leaves me from 50, 5 remaining, so that's 5 over 50. So the probability that they study maths or English, in this question it's important to note it doesn't exclude both, so that means we could be talking about the students in this segment, the students in, so the maths students alone, the maths and English students, and the students who just study English. So I'm looking at those 3 elements, and so what I get is 20 plus 10 plus 15 all over 50, which we totaled up a moment ago because I needed to find that outside amount, and that's 45 over 50. And so if you want to cancel that, you can divide top and bottom by 5 to get 9 over 10. I hope that all made sense and that you understood that example. So moving on, we're going to look at some more theory linked to Venn diagrams. First of all, a little bit of notation, etc. We've got the complement of events. The complement of an event A is denoted by A apostrophe and is the event not A, or that A doesn't happen. Okay, so we can have A, which is the probability of A, which is the probability of A happening, or we can have probability of A complement, which is a probability of A not happening. So since you can either happen or not, the number of ways A can happen and a number of ways A can't happen will total up to be the total number of outcomes. And we saw this notation in the GCSE Essential Knowledge Recap. So what that means is the probability of A happening plus the probability of A not happening is always 1. And a simple example of this is if you think about flipping a coin, probability of a head is a half, probability of not getting a head is also a half, adds up to 1. Roll a dice, probability of rolling a 6 is 1/6, probability of not rolling a 6 is 5/6. Add them together, we get 1. Okay, so it's a fairly straightforward idea. Let's have a quick look at Venn diagrams then and how we can use them. Probability, so here's some notation. This notation here, A and this funny N, I almost kind of, in bad maths moments, think of this as and, because it almost means the same, but actually mathematically what we're saying is A intersection B. And it's the probability of both event A and event B occurring. So what we're talking about is this section here. So we've already been working with this section. This represents the area of where both A and B happen. Okay, so it must happen both at the same time. Now, this is another really important bit of theory, the union of two events. Okay, so these link quite closely to the and or at GCSE, but are slightly different. So just be careful with them. The union means the probability of either event A or B or both occurring. So we can have the event A, which would be this area here on its own. You can have event B, which would be this area here. So we're just talking about them on their own at the moment, or both, which would be this central area. So when we talk about the union, we're actually talking about this whole area in the 3 segments of the Venn diagram. And what you'll find is when you work with intersection, when we have just a standard kind of Venn diagram with 2 sections in it, an intersection, so here's our intersection, it will always relate to one area within the 4, because there will only be one area where both of these conditions are satisfied at the same time. When we're talking about the union, it will always relate to 3 areas, because it will relate to, for example here, the 2 areas of A and the 2 areas of B, and although that links kind of to 4 areas, we have this overlap here, so this area in the middle is counted twice. Now this idea links neatly to our next little bit of theory, the addition formula. This is probably one of the most important formulas you're going to learn for S1, because this formula is kind of like a magic formula in that it works in all cases when we're dealing with probabilities and calculating probabilities within set theory. So the addition formula states that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. So, I mean, if we have a look at this, probability of A union B, so A union B, we saw a moment ago, is the probability in X in A, well, these 3 probabilities, these 3 sections here added together. So how is that calculated? Well, the probability of A, let's highlight that, that's this section here. So this represents our probability of A. We then have probability of B. Sorry, should have been a different colour. No, I can't get a different colour. Not to worry. We'll use a pen. Probability of B, which we'll highlight using this pen. This represents everything in this circle here. And then we're going to subtract the probability of A intersection B, which is this bit here. And the reason for that is because if you look at what's happening in these probabilities, I add X and Y from probability of A, I add Y and Z from probability Z. You can see I add in this probability for Y twice. So it's where this overlap is, and you can see it contained with those two rings, and I've done it in blue. We subtract that away once because actually I've counted that middle intersection twice. Now this is a really important formula because this works in all situations when we're working with set theory questions. Okay, now you're not expected to prove this, it's just nice to understand why we've got the addition formula. And this sometimes can be arranged. You may see it's in used and stepped straight to in some textbooks, etc. It's just a quick rearrangement by adding A intersect B and subtracting A union B. Sometimes you may see it written as this. It's not a different formula, it's exactly the same formula. We've just subtracted A union B from both sides and added A intersect B to both sides. Okay. So if we push on and just look at a couple more Venn diagrams, just so we make sure we understand the different regions of the Venn diagram. So start to use the complement notation now. So probability of A complement intersect B complement. So this is the probability of both event A complement and event B complement happening. So if I just use a blue pen a second to represent A complement, so I'll underlay A complement with the blue pen. So A complement are these two regions outside of the event A. If I use a red pen just to identify where on the Venn diagram that B complement occurs, so B complement is the regions outside of B, so that would be this region here and this region here. The intersect is where both occur. So the intersect is quite a big region, so I'm not going to colour it in, I'm just going to highlight which region we're talking about. The intersect is all of this region actually outside of A and B. Okay, so it's where both overlap and occur at the same time. Okay, hope that made sense. So let's have a look at something slightly different. So this time I've got the probability of A complement intersect B. So let's work in a similar way. Let's use red to represent A. A complement is still this region outside of those two regions outside of A. If I use blue now, the event B occurring, well, these are the two regions inside B. Where is the intersect? So where does both A complement and B complement occur? Well, we're talking about the region with the two dots in. And so I'm looking all around inside this region here. Okay, so I hope that makes sense. Let's have a look at a couple of other regions. This is always a tricky one. Okay, so union, remember that we're looking to count up all the events, all the regions which are included in this bracket here, because it's a union. So it's a union, it's everything that happens. So it's either so it's the probability of either A complement happening on its own, or B complement happening on its own, or both occurring. So starting off with, let's go for red for A complement. A complement would be the two regions again outside of A. B complement, using blue to represent that, that would be our two regions outside of B. And now I'm looking to include, for the union, all of the regions which have a dot in. So essentially, I'm including everything inside the Venn diagram, because I've got the outside region where the two dots are. I've got the A bit on its own, because that's got one blue dot in. I've got the B bit on its own, because that's got one blue dot in. And I'm talking about all of the region, so just using some stripes that I have shaded, is everything apart from this little bit in the middle, the intersection. Okay. I hope that made sense. We have one more Venn diagram just to have a look at and try and understand how we take readings from. Probability of exactly one of A or B. So this is a description here, just exactly one of A or B. So what we're looking at is, actually we can use a highlighter directly for this. Exactly one of A or B, so I either want it in this region here, because that is just A and A on its own. Just quickly shade that in. Okay, so we're looking at the probability in this region here, or B and just B alone, so that is just this region here. And so that is what we mean from the Venn diagram there, the regions we're talking about when it's just A or B, exactly one of them, or A or B, but not both. So we're just, again, excluding this intersect. Okay, feel free when you're working to just go back or refer to diagrams to help you learn the different regions of the Venn diagram. It makes more sense to understand the notation and how it links to the Venn diagram rather than just trying to learn the pictures. But the visual representation should hopefully help the formulas to stick. So what we're going to do now is we are going to have a look at a couple of examples to try and apply this theory. So we're told, given that probability of A is 0.4, probability of B is 0.5, and probability of A intersect B is 0.1, we want to find all of these different probabilities. Okay, so this is a slight change in what we've been looking at so far. The way we work with these probabilities is exactly the same as we did earlier when we was being described kind of those students who were in maths classes and English classes. Essentially, what we're going to be working with in the S1 exam and most problems is completely context-less examples. So we don't know what the event A is, we don't know what the event B is. They just represent some sort of event, and all we know is the probability about them. We have to get these proportions into the Venn diagram. Okay. Now, as before, the intersect in the middle, that is the most important bit. Now, what we was told in the question was that the probability of A is 0.4. We was told the probability of B is 0.5, and we're told the probability of A intersect B is 0.1. So when I work through this, starting with the middle, the intersect, that's our key, as before, I can put in a 0.1. Now everything in the A oval needs to add up to 0.4, so it's the difference between the probability of A and the intersect. So the probability here is 0.3. Same sort of idea for the remaining part of B. It must total up to 0.5. So we're just going to take the proportion that's contained within the intersect out already. So I get an answer of 0.4. Now, the total probability within this Venn diagram must total up to 1. At the moment, I've got 0.3, 0.4, 0.8. So the remaining part must be 1 minus 0.8, which gives me a probability of 0.2. Okay, so let's work through this. I'm just going to use a blue pen to kind of identify the different areas we want to use. Probability of A union B. A union B was all the ones in A, all the ones in B, and we can count where we've doubled up on the spots as well. So I'm looking at the total of 0.3, 0.1, 0.4. So we don't usually have to write this, but what I want to do is just put it in there so you're 100% clear how I'm calculating this. And so I get an answer of 0.8. Okay. Now, let's have a look at B. B is the probability of A intersect B complement. So probability of A, I'm looking at the regions contained with A. We then want to do B complement, so that's the regions outside of B. And the part I'm interested in is where both are happening, the intersect, so that's where I've got my 2 dots, and so I'm just looking at a probability of 0.3. Okay, so let's look at the next question. Probability of A complement intersect B complement. So A complement outside of A, so put the 2 dots in those 2 regions. B complement outside of B, so 2 dots in those 2 regions. And so it's the intersect. I'm interested in the region that contains both dots. It's this area outside of the Venn diagram, so a probability of 0.2. And remember I said earlier on, notice that for a union, I'm looking at 3 sections of the Venn diagram when we're just talking about 2 events. For an intersect, it will always come down and be 1 single section of the Venn diagram. Okay, so let's look at the next question. Next question says, let's find probability of A complement union B. Okay, so A complement outside of A again. B, well, that's going to be the 2 sections inside B. And because it's a union, I'm interested in the 3 regions that I have identified. So I've got this outside region 0.2 plus the intersect region, which is 0.1. So that's the 2 on their own. And where it's both true, we've got this partial part of B, which is plus 0.4. And so we get a probability of 0.7. Okay, I hope this is all making sense because we're now getting on to the final one. Okay, and so finally we want to find probability of exactly one of A or B. So exactly A, just one of A, but not both, is this region to the left of the intersect here. Exactly one of B is just this region to the right of the intersect here. So I'm looking at the total of those 2 regions, which is 0.3 plus 0.4, which is also 0.7. Okay, I hope that all made sense because now I want you to try one out for yourself. So what we have here, given that the probability of A equals 0.2 and probability of B equals 0.4 and probability of A intersect B is 0.15, we want to find all these different probabilities. Please draw yourself a Venn diagram and fill in a Venn diagram before trying to find these probabilities. So pause the recording now and have a go at the question. Okay, welcome back. Let's have a look at the solution for this then. So it's told probability of A equals 0.2. It's told the probability of B is 0.4. And the probability of the intersection was 0.15. Okay, so put the intersection in first of all, 0.15. What this region and this region to add up to 0.2, so this would be 0.05. This region and this region to add up to 0.4, so that would be 0.25. And then the outside region is whatever's left over from one from these 3 sections. So I get 0.45 for these 3 sections, so outside should be 0.55. Okay, A union B, well, that's the region that links to A. This is the region that links to B. The union is all 3 sections, so 0.5 plus 0.15 plus 0.25. I'm not going to be able to fit it in, so I'm just going to have to put the answers in, is going to be 0.45, which we calculated a minute ago in order to find that outside probability. Okay, so probability of A complement intersect B. Probability of A complement intersect B. So looking at A complement. A complement is regions outside of A. Intersect B, regions inside of B. So I want to know where both are happening, and it's this region where 0.25 is. Okay, so let's have a look at the next one. Next one says A complement intersect B complement. So region outside of A, region outside of B. Where is both happening? It's the outside region, so 0.55. Okay, and then finally probability of A union B complement. So we're talking about the region inside of A. B complement is the region outside of B, so outside and outside. So we're talking about the three regions, 0.15, 0.5, which is 0.2, plus the 0.55, which gives me 0.75. And finally, exactly one of A and B. A or B, sorry. And so exactly one of A is a 0.05, exactly one of B is a 0.25. So when I total them up, I get an answer of 0.3. Okay, I hope this is all making sense. Now, just a note, while I've been doing the spots to actually kind of like help you get to grips with the union and the intersection, I'm not going to continue to do that anymore, because obviously when you actually end up answering 5 questions, if you're using a pen in the exam, I mean, fantastic if you've got a pencil to kind of dot the regions and keep track of what you're doing, you can do that. But if you're using a pen, you're going to have lots of dots, and so it's going to become a little bit confusing. So all I'm going to do is just identify the regions with my pen by circling them like this from this point onwards. Okay, so let's have a look at example 4. I've got the probability of A is 0.5, probability of B is 0.3, and the probability of A complement intersect B complement is 0.4. And so I want to find A union B, A intersect B, and exactly one of A or B. Okay, so we're told probability of A equals 0.5, probability of B equals 0.3, and probability of A complement intersect B complement equals 0.4. So we always have to start with the intersect region. Unfortunately, this time the intersect isn't this central part here. It's actually the outside part. So what I'm looking at here is this area here is 0.4. Now at this point, I get a little bit stuck because I don't know how probability of A is distributed between these two regions, and I don't know how the probability of B is distributed between these two regions. So follow the questions, because quite more often than not they are structured in a way that will lead you through the question, simply because it makes life easier. A union B are these 3 remaining sections here. What I know is if I add these 3 sections with this section here, it should be equal to 1. So A union B will be 1 minus 0.4, which equals 0.6. Okay, now while that might not seem particularly helpful to have the 0.6 for these 3 regions, because I still don't know how it's distributed between those 3 regions, what I can do is I can now use the addition law, so that's the probability of A union B, equal to probability of A plus the probability of B minus the probability of A intersect B to find A intersect B. So I know A union B we've just calculated is 0.6. A and B, so A is 0.5, B is 0.3. I don't know what the probability of A intersect B is. What we're going to do is we're going to rearrange this equation. So I'm going to subtract 0.6 from both sides. I'm going to add the probability of A intersect B to both sides, so that I end up with the probability of A intersect B equals 0.8 minus 0.6, which is 0.2. And at this point I can actually complete my Venn diagram, because I now know the central part is 0.2. The part of A here must be 0.3, so it can total up to 0.5. the part of b here must be 0.1 since it totals up to 0.3. And then so finally, when it says find exactly probability of exactly one of A or B happening, I get 0.3 plus 0.1, which is 0.4. And so I should put the probability of A intersect B up here as well to be complete. Okay, I hope that all made sense, because it's now time for yourself to have a go on the last example of this week's video. So we've got the probability of event A is 0.4, the probability of event B is 0.45, the probability of that neither A or B occurs is 0.2. We want to find the probability that exactly one of A or B occur. So it makes sense to link this to the notation we've been working with. Draw your Venn diagram, use your rules that you need to use, and then complete your Venn diagram so that you can find the probability that exactly one of A or B occur. So I want you to now pause the recording and attempt the question, and press unpause when you're finished. Okay, so welcome back. Let's go through the solutions. So we had the probability of event A was 0.4, so just putting it into notation, we just simply need to write it as that. Probability of B was 0.45. So all I have to do is put it into notation like this. And it says a probability of neither A or B occurring. So this is actually the probability of A complement intersect B complement, which gives you it's 0.2. So actually we follow a very, very similar sort of approach to the last question, a little bit unstructured on this one. So this is 0.2, so what I know from this is then in that case probability of A union B must be the remaining amount, because it's these three sections here, must add up to 1, so I get 0.8. Using the addition rule, probability of A union B equals probability of A plus the probability of B minus the probability of A intersect B. So I know probability of A union B is 0.8, probability of A is 0.4, probability of B is 0.45, minus probability of A intersect B. Exactly the same operations to rearrange and solve this. I'm going to subtract 0.8 from both sides. I'm going to add probability of A intersect B to both sides. And so I get probability of A intersect B equals 0.85, take away 0.8, 0.05. So just fill that in now into my Venn diagram, because I know the central bit is 0.05. The remaining part of B to add up to 0.45 must be 0.4. The remaining part of A to add up to 0.4 must be 0.35. And so then exactly one of A or B is going to be 0.35 plus 0.4, which is 0.75. Okay. Well, I hope it all made sense as to what a Venn diagram is and how we use a Venn diagram and all this notation. From this point, if you have a go at the set theory exercise I have sent you, and then once you've had a go with that set theory exercise and you understand it, have a go at assessment 2, which I've also sent you. Make sure that you've worked on enough of the set theory exercise to make sure you're confident before trying out the assessment 2. Just doing assessment 2 won't be enough practice. You need to really get to grips with the ideas, and then do assessment 2. And then next Friday, which is going to be the 22nd of January, I will go through this with you. Okay. Hope you enjoyed the video, hope it made sense, and I hope you now understand Venn diagrams and how to use them.